Now consider the following output maximization problem, which is another type of constraint optimization problem. The question is to find the most output given that, let's write it out. What is the most output, which we usually represent with the letter Q, if you remember, given that we have a budget of say $1,400. When I say budget, what I really mean is cost here, right? So this is the cost and technology. So what is the technology, the production technology that we use? Let's say that the technology that we are using is Q equals F of, again, we are using two capital and labor, two factors of production. However, the technology is now represented like this: 10 times K to the power 1/3 times L to the power 2/3. All right, so this is the, given that technology and given that we have a budget of $1,400, how many units of output can we produce at most? Also given the fact that, say, capital and labor and let's say that capital and labor cost the same amount as they did in our previous cost minimization example, namely rental rate of machines is $9 or capital, and labor hour, each hour of labor is $16. So given these and the fact that we have $1,400 budget, and this is the technology that we are utilizing, and this is the technology, what is the most output that we can produce? What is the best combination of K and L as a result, right? So if you want to write an equivalent formalization of this, so the question basically is asking you to maximize output, which is just 10 times K to the power 1/3 times L to the power 2/3, subject to what? Where by changing K and L, obviously, by changing the factors of production K and L, subject to the following constraint, namely that cost, which is, you want cost to be at $1,400. So $1,400 is equal to 9 times K plus 16 times L, and also the fact that capital and labor are both non-negative. They have to be greater than equal. So this is the actual mathematical representation of this problem of maximizing output. All right, so this is the output maximization problem we want to solve. I will directly dive into the problem this time rather than spending time on trying to go over what are the meanings of the terms, how do we express this, and so on. So the solution to this problem is actually very straightforward. Just like we did in the cost minimization problem, we want to first of all construct the Lagrangian, which is L is equal to, just write the objective function here again, so 10K to the power 1/3 times L to the power 2/3 plus a penalty function times the constraint. Only one of them. We don't need the other two constraints. Only the $1,400 thing. And all we do is we just move expressions to one side of the equation. Doesn't matter which one you move. I think in the cost minimization, we moved the constant to the other side. This time, let me do the other way around. Let me move these two expressions to the left-hand side. So that will give us 1,400 minus 9K minus 16L, and close the parentheses. That's it. That's the Lagrangian. Now we have a business to do. We need to take the partial derivative of the Lagrangian with respect to the two inputs, as well as with respect to the lambda. But it turns out that it gives the third equation will directly be the constraint itself. Let me just highlight it. The constraint itself will become the third equation. So I don't have to really take the derivative of just two partial derivatives, basically. So take the partial derivatives, set them equal to 0. Let's do it. So if you take the partial derivative of the Lagrangian with respect to K, meaning that K is the variable, L is a constant, just like the number 10 it is. So I'm going to take the derivative of the first. So we need to first identify where the K's are, which is here and here. Okay, so therefore the derivative will be, just move that 1/3 to the front, keep the 10, keep the L to the power 2/3. Now for the power of K, it will be down by 1, so it's minus 2/3. You guys see that? And then we have to take the derivative of this one, which is minus 9. There's also a lambda here, minus 9 lambda. That's it. You do pretty much the same thing for L by just changing the L. So by just taking the expressions, the derivative of that, everything else will be just 0, as you all remember. So it is 2/3 times 10 times, keep the k as it is, 1/3, and now L reduce it by 1, so which is minus 1/3, and then we have plus lambda times minus 16, which is minus 16 lambda. There you go. And like we said, the third constraint will remain. Now what I will do is I will just move these two expressions to the left hand side and then take the ratio of these two expressions. You know what, I'll just do it right away. So this thing is equal to 0 is the same thing. Implication implies that that thing is so I just moved the 9 lambda minus 9 lambda to the left hand side. There was a 0, now it's 9 lambda. So now I can just take the ratio of these two expressions. Let me just go ahead and use a different color. I want to take the ratio of these to the left hand side and the right hand side. So therefore this implies, or maybe I should write therefore. So therefore what we have on the right hand side, we have 9/16. Now what's left on the left hand side? The 10s will cancel, the 3s will cancel. Certainly we will have a 1/2. 1/2, and then what else do we have? We have, well, we have an L to the power minus 1/3. I can bring it to the numerator, it will make an L, and then that minus 2/3 goes to the denominator, becomes k to the power 2/3. Adding the 1/3, it's k. So therefore we have L over k. Do you guys see that? And finally, if you rearrange them, so for instance L in terms of k, L is going to be equal to a 9/8, if I'm not mistaken, 9/8k. That's it. That's the optimism. Now we need to plug this into the original constraint, namely that cost should be $1,400. We don't want to spend more than $1,400. Let me rewrite that. So given that 1,400 is equal to 9k plus 16L, I'm going to replace the L now with what I got here. 9 times k plus 16 times 9k over 8. Right, so substitute that. The 16 and the 8 cancel, there's a 2 there, so that's just 2 times 9 is 18 plus 9 is 27, 27k. So 27k is equal to 1,400. Dividing both sides of this expression, wait, was the original, oh yes, okay, I changed it. Okay, in my original notes, I did it with 4,000. That's okay. All right, so now we change the question, 1,400. Fine. Okay, so 1,400. So what I will do is divide both sides by 27. So finally, k comes out as 1,400 divided by 27. And if you want, this is roughly equal to, let me quickly do it. 1,400 divided by 27 is roughly 51.85. Hours of capital, and as a result labor will come out as 9/8 times capital, which is 1,400 over 27, but the 27 and the 9 they cancel, so there's a 3 left over there. The 1,400 and the 8 also simplify. I think they are both divisible by 4. So this one will be a 2 left in the denominator. In the numerator, there will be a 350. Wow. So it is also divisible further by 2, I guess. So there's really 175 left here. Awesome. All right. So therefore, the final expression is 175 all divided by 3, which is roughly equal to, let me check, 175 divided by 3, 58.33. 58.33 units of labor, hours maybe, right? Hours. Let me just make sure my calculations are correct. 9 times, I don't want to make a silly mistake, divided by 8 and a further divided by 27. Yes, 58.33. And now that I know my capital amount, my labor amount, now we can find the optimal production, because that was the question, right? The question was to find the optimal output. What is the most output that we can produce given a certain budget that we have, $1,400 budget? It turns out Q as a result, so therefore Q, which is 10 times k to the power 1/3 times L to the power 2/3, I think it was, is equal to 10 times, so replace k with whatever we got here, 1,400 over 27 raised to the power 1/3 times, and then labor is 175 over 3 raised to the power 2/3. Now remember that that's the shape of our function. All right, and now the rest is just a calculator business. So let me just go ahead and do the calculations here. So 1400, oops, let me do it. 1400 divided by 27, again 58.85. Now I want to take the cubic root of that. Your calculator, scientific calculator presumably, will have a function where you can take the exponent. Exponent 1/3, I can just 1/3, close parenthesis, equals. So that one is 3.73, believe it or not. And actually, I want to be more exact, 72.9 to be more exact. Let me add one more decimal place of accuracy there. And then for the last one, it is 175 divided by 3. And then I want to take it to 2/3 power. So I can square it first, and then let me raise it to the 2/3 power. 1/3 power now. 1/3, close parenthesis, equals 15.04. 041 to be more exact, 15.041. And now multiplying these results, we get 10 times 3.729 times 15.041 equals 560.88 units. That's it. So this is the maximum amount of units that we can produce, given that we have a $1,400 budget, and given the fact that capital costs, machine hours cost $9 an hour, and labor costs $16 an hour, just like in the previous example that we solved. Now, in the next video, I'm going to go ahead and use Excel to solve this problem yet on Excel.